teach a little bit of atom probe data analysis through YouTube videos, through live streaming, and this was mostly done with my research group. So I'm a W1 professor, which is kind of like an assistant professor here in Germany, and I'm running an atom probe group. And of course, I'm trying to teach my my PhD students and also master students, so on and so forth, how to use the atom probe and how to do proper data analysis. Of course, that means, going beyond what you can usually do or what you can do with commercial software, mostly because we'll work a lot on interfaces and we'll work on weird chemistries and so on and so forth. And you really need to be able to dig deep into the data to really get to the bottom of things. So when I was doing my presentations, the main criticism was, of course, that he couldn't see all that much, or that I was moving too fast, and it was mainly because I was sort of working with the audience. So I thought I'd make a series of videos. Now I actually have a little bit of time on my hands, and a little series of videos that shows you, everyone that has not had any experience in doing any analysis by themselves, on how to do atom probe analysis using Matlab. Now, the reason why I use Matlab, I don't just use Matlab, I also use other programs. Some of those you will see later on in the process. But the main reason why I use Matlab is because it's an interpreted language, which means you always have the code going with everything, so you can go and look into the code and see what it does, alter things, make it work for you. And you can always also dig deeper into the data and just be very flexible. That's of course the case with any program where you use command line rather than graphical user interfaces. But of course, the downside is it's not as visual, so you don't get everything nice and prepared for you. But you gain a lot of flexibility. And with Matlab, because it's a very high-level language, you can code stuff that you need to do your analysis very, very quickly. And you will see that you get various components of various, I would call it a toolbox of Matlab programs you can use as a basis for your analysis. And I will show you how to use them. I show you how to load in atom probe data, show you how to deal with it, what sort of components are to the atom probe data, and what you can do with it. This is supposed to be suited for everyone that has no experience in Matlab either, so we'll also go through the Matlab basics while we're going through it, and I'll try to keep it to sort of 15 to 20 minute chunks at the most, so that you can take certain aspects of those things when you need them. And the first thing is, of course, how to get started with Matlab and how to get your atom probe data loaded in. So a quick tour through Matlab and the way I've set it up today. So you've got your ribbon here that gives you all sorts of options like creating new scripts or new variables and so on and so forth. But we will mostly move through the command line. So we'll occasionally use this here, maybe also for making plots. But again, this is usually better done through the command line. So on the left side here, you will see the command history. So if I'm going a bit quick, or you might lose some track here on the command line side, they can also see a bit of the history here in the command history. Then here on the right side, we've got the workspace, which is where we're going to see the variables. Most of the variables, we're going to try to stay consistent with the naming. So we're not going to have too many issues remembering which variable will be called what. And I'll go through that in a minute when we're starting to load atom probe data. Here we've got the current folder. Current folder means you can see what programs you've got available, what scripts you've got available. And we're going to have most of them just in one folder. And we're going to navigate from that folder. Sometimes also we will need to unlock some subfolders where we have routines in that it would otherwise clutter our folder structure. So Matlab by itself, of course, doesn't know how to load atom probe data because it doesn't know what data formats we have. Of course it doesn't, so we need to tell it how to do that. And for that, I put a series of AtomProbe tutorial code that was used for my last AtomProbe tutorials. I've put them on GitHub. I will post the GitHub link in the description to the video. And you're going to be able to download all the different code that you need to do the analysis there. So you can see there's all sorts of things there, like turntable animation, which is a pretty handy one. Which is just taking your AtomProbe data in the view that you've put it in your window, and then it rotates it by 360 degrees, takes a frame in certain intervals, and packages that up into an AVI file that you can use in presentations or in papers. But the most basic ones are, of course, read pos and save pos. So the dominating file formats that we have right now in AtomProbe tomography are called pos files, which stands for position, I think. I've never asked, but anyway, which has 4 entries, X, Y, Z, and the mass to charge state of the ion or of the detector head calculated from the time of flight. And this is what we're mostly going to use for simple analysis. It's another one called extended pos file or EPOS file, which contains all the experimental data as well. We're going to use that probably sometime later during the analysis series, but they can also be loaded through the same routine. You'll see that. And the 2 components that we need, firstly, to interpret our AtomProbe data are so-called POS files and range files. So you probably, if you're watching this, you already have at least some experience with AtomProbe tomography. So you'll know that there is that you identify certain ionic species, usually by going into the mass to charge state histogram and saying, okay, from mass to charge state this to mass to charge state this is this and this ion. Of course, this produces some issues with overlaps and so on and so forth, but that's the way we do it right now. So to load the AtomProbe data in is actually fairly simple. So I'll just create a variable called POS. This is a new variable. So you can see in the workspace, everything's empty right now. We don't have any variables. And I'm going to assign this variable a value. And this value is going to be created by read pos. Okay. Now the read pos command is a file loading command, and you can type in a file name. So if you know what the file name is, or you work very often with the same file, then you just type in the string of the file name. Like you would start a string and then, I don't know, C, blah, whatever, .pos. But if you leave that empty, it will come up with your system dialog to find the POS file. Now, I've got a Mac, so I can just drag and drop in this case very easily. Can just drag and drop very easily. And I've got some data here, so that's called whatever.pos. You can see the EPOS is already here as well. It's a cobalt-based alloy. And then I press OK. And then it loads in the data. So this is a medium-sized file, so you can see it's got a size of about 0.5 gigabyte. We've got larger ones, we've got smaller ones, but I don't want to show you only how to deal with very small files, because maybe you've got very large files, who knows. Anyway, so now we've got the AtomProbe data loaded, and actually it's all there now. So if you go in here, you can already see we've got the 4 columns. And these 4 columns represent X coordinates, Y coordinates, Z coordinates, and the mass to charge state. So you can see there is a lot of atoms with relatively similar mass to charge states. Anyway, we don't need the visualization for now. Now, of course, the question is, now we've got all the data loaded, but we just want to select a specific species or a specific range, as we call it. So I'll just call a variable MC begin, and we'll take it 26.9. So for example, I know that aluminium has a master charge state usually of 27 Daltons. So if we go from 26.9 to 27.5, we're probably going to catch most of the aluminium peak. Of course, you can also do that in a more graphical manner in IVAS, and you probably have done that. So I'll show you how to deal with that straight after. Anyway, so you can see now, oh, I've forgotten the semicolon, so it's plotted that out, which for this variable doesn't matter all that much, but you don't want to do that for a pos variable because it will literally print all the couple of million points that you've got in your pos file. And then we'll go MC end, master charge end equals 27.5. Okay. And now I'll just call my variable aluminium positions equals, okay, so the equal we have here, that's an assignment. So one single equal in Matlab means we've got an assignment and the variable is being assigned whatever value comes to the right. So we want to have a subset of the atomic positions, which are in this array called POS. This variable that is an array, which contains 32 million atoms roughly, and of course each atom has 4 entries: X, Y, Z, and master charge. Okay, so in order to get the aluminium positions, we now need to get all of the entries from here, and that's of course not all of the aluminium, because the aluminium cannot be aluminium plus, aluminium 2 plus, and aluminium 3 plus. But for now, for simplicity, we're just gonna get one. We're just gonna get one range. So what we need now is all the entries out of the POS file. So we're going by columns now. So when we reference a variable, we've got that's a two-dimensional array. We'll have 2 entries. So first one is the column, and the second one, so this is the column, and this is the, this is the row, and this is the column. Okay. So we only want those rows that have a mass to charge between 26.9 and 27.5. So we'll do selection for the rows, which means here we'll need to go and say we want the 4th column. Okay, so what we're doing now is actually creating a logical variable in this entry, and that logical variable determines which entries from POS we're actually selecting. Okay, so the logical variable is of course I can do it this way now. The logical variable is of course based on the POS as well, because in the end it needs to have as many entries as POS has rows in this case. So we'll go POS, and we'll take all rows, but only the 4th column. Okay, so this is what this means. And this needs to be larger than MC begin. But also, and that's what the end does. So this is the end symbol. And POS 4th column, we also need to be smaller than MC end. Okay, and so this is now the logical variable that we have, but we want on all 4 entries. So all entries is just the it's just the colon here. Okay, so if you use the colon operator, colon means take all entries. Of course, we need the semicolon. We need the semicolon at the end so it doesn't plot everything. This is actually all we need to create that aluminium POS variable, which is, again, disclaimer, I know it doesn't contain all aluminum atoms that are in the data set that we have identified. But working with range files we'll do in the next video. Okay, if I... Yep, okay, sorry. It's not the end operator, it's the end operator. And now we've got a new variable here called ALPOS, which has roughly 1.3 million entries. So out of the 32 million atoms, apparently there were about 1.3 million aluminium atoms that came off as aluminium 1+. Okay. Of course, you can do it, and now the aluminium POS actually still contains the fourth column here, which means within the aluminium POS you can still search what master charge that aluminium ion did exactly have. If you don't care about it and you just want the atomic positions, you could type 1, 2, 3. So this just means first, second, third column. And if I do that, you can see here, now it's a three column vector. I usually keep all 4, so I'll go back to the first one, just because if I later need to concatenate and do some other operations, you know, I don't want to throw anything away that I don't need to throw away, and it doesn't chew up all that much data. Okay, and the last thing we're going to do in this video is to visualize. So now we've got the aluminium POS file and we want to visualize that, and that is actually fairly simple using the scatter command. So I've got I use it pretty often, so I just need to do autocomplete. But the scatter command, what the scatter command does is it plots a point cloud, which you can give, you can change its color later then, you can rotate it around, and you can do all sorts of fancy things. In order to be able to use autocomplete all the time, what I usually do is create a variable called sol, which stands for solute, and in this variable I put the solute I'm currently working with. So just imagine this is a data set which contains aluminium and tungsten and rhenium and God knows what, half the periodic table. Then whenever I switch to working with a different solute or a combination thereof, then I just use this variable and throw whatever data I have into that variable, and then I can just reuse all the commands that I use all the time. So in this case, I'll just use solute equals aluminium POS. So again, this is putting the data from aluminium POS into solute, and now we've got that new variable. Now I'll redo the the scattering command. And one thing you will notice is that plotting 1.3 million points is probably not that useful, even if it works, just simply because you're not going to see much, okay? That's a lot of points floating around. So the second thing we're going to do is we're going to randomly, out of this sol thing, we're going to pick a number of atoms, okay? So we say we want to pick 10,000 atoms out of it, or 50,000 atoms out of it. Or you can pick a percentage. You can say, I want 5% of those. A percentage is always good if you're comparing a couple of different atomic distributions, just simply for the reason that if you always downsample them to the same amount of atoms, if you show that in a paper or a presentation, people will just assume that the concentration of the different species is the same, even though it's not. Anyway, so to do that, I'll just create a variable called sample, which is a random sample. So this is just a vector of numbers from 1 up to the length of the solute. So up to 1.3 million, 7, whatever, yeah. And we want 100,000 entries, maybe. Right now we don't want 100,000 entries, we want 10,000 entries. By the way, the new graphic systems in Matlab can finally actually display a lot of atoms, I don't know, 100, a million probably without choking too much. The old system wasn't, if you have a Matlab version that's older than 2014, I think, it didn't deal all that well with larger point clouds. Anyway, now it does it pretty well. So what this now is simply a, so you can see a vector with numbers in there, and it just says, okay, out of those 1.3 million, we're picking number 882,277, and so on and so forth. Now we can use the scatter command. So we use the scatter3 command because it's three-dimensional. And in the scatter3 command, you've got x, y, z. And you can also have display properties that you can type in. And of course, this is a little bit annoying sometimes because you need to type all the three coordinates in separately. But anyway, Matlab makes it. Sometimes it's not all that logical, but in this case, okay, we've got to live with it. So what we want is solute, and from the solute, the first column. So this is the x column, and then from the solute, the second column. Again, remember this is this means we're taking all rows, then comma, and this is the second index, which means we're taking all columns. And then solute 3. Also, what I'm going to type in is point, so otherwise it's going to appear as circles. Now I'll leave it out. I'll leave it out, and we'll just take the simplest version of the command, and then later I'll show you how to use some extra things to make it up. Did I forget about something? I did. What did I forget? Oh. I opened a bracket here. God knows why. Anyway. So now we've got this scattered plot here. Oh, now we've actually, sorry, my bad. We have actually displayed all atoms now, but you can see even with the 1.3 million atoms, it gets a little bit slow, but it still works. Anyway, it's not what we want. We wanted to have the sampled version of it. So we'll go scatter3, solute, and out of the solute, we want just the sample. And then, of course, first column. And then we can just go and repeat that twice, and just change it to second and third column. So now we've got a scatter command where we've used the solid atoms, but just a sample out of the solid atoms, and then the first column, which is the x, and then so on, and then for y and z as well. Now, if you change the solid, so if your solid vector, if your solid matrix, the number of solid atoms changes, of course you need to recalculate the sample, because otherwise it might contain indices that are higher than the number of atoms you have in that variable. Anyway, now that's a whole lot quicker. But what you can see here now is, even when I rotate, you can see that there is some precipitates in there. But Matlab also always tries to resize it so it's got the same height and width. This is pretty annoying. We don't want that. So there's a command for us to get rid of that, which is called axis equal, which I'm pretty sure you can do by just going into view axis equal or something like that. Anyway, I like to type it in. And now we've got the display here. The next thing I'd like to do is opening the plot tools. And in the plot tools, we'll change the marker to a point. This is usually a lot more convenient for atom probe data. Anyway, this is now a display of the aluminium, and you can already see there is a precipitate here which contains aluminium. I think tantalum would have the strongest partitioning in that data set. And now if we want to actually animate that, that's very simple. So all we need to do is type in animate, not isosurface, we can animate isosurface as well. Oh, what did I call the program? Turntable animation. Sorry, turntable animation. So this means how many steps. So the step is 0.5 degrees. Sorry, we could probably do it this way. So degrees and the file name. And the file name I'll just call test. Now, if I press enter, you can see it starts doing the animation, grabs a frame at each interval of 0.5 degrees, and then creates an AVI from that. Okay, done. This obviously gives you a little bit more freedom because you can. Yep. Basically, you could, for example, move it to here and have it rotate, or you can move it to here and have it rotate. So you can use whatever perspective you want, and it will just rotate starting from that perspective. Usually, a good thing to do is to use XZ view or something like that, so that you can be consistent. Anyway, so we have got that here now. So you can see we have got the test AVI. Open outside Matlab. Whoop. And we've got a nice animation of our data. Don't save the converted version. So here, just to show you, the data size is the size is then 25 megabytes, and I think that's a fairly reasonable size. You can go into that program and change the size you want, so you can down render and so on and so forth. But yeah, good. So now you know how to load data into Matlab and how to choose a range and how to do a quick animation. So I hope that already helps you a lot, and this is the end of the first tutorial.